Okay, so last week on Wednesday we talked about importance of simulation, and we talked about the industrial revolution that we have had so far. Now we are in the era of the fourth industrial revolution, where artificial intelligence, simulation, virtual reality, these kind of things are really important, especially because there are a lot of data and really doing things physically or experimentally is expensive. So, um, anyway, simulation is really important, at least in process development of chemical industries, including biomass conversion. So we talk about some kind of features that you can gain from simulation. But now I want to talk about something really interesting about importance of process scale up, process simulation in order for process scale up. Before we touch that point, let's go through a couple of uh, unsuccessful industrial processes. So I'm going to just give you some examples and then you will see why we are talking about new approach in process to scale up that where simulation is important. So the topic of today is a new approach in process to scale up, learn from unsuccessful industrial processes. So uh, one, we are going to just cover two cases of unsuccessful scale-up approaches or practices in the past. One of them is Lycra process chain, where it was about producing tetrahydrofuran THF. This is a product that is also produced from biomass. Conventionally, this product is supposed to be produced from butane, C4H10. So C4H10 is like a 20 cent per kilogram in terms of price, but the final product is going to have a price about 70 to $50 per kilogram. So making this product is really interesting, really economically attractive. So of course, uh, by looking at this kind of price valorization, uh, companies are interested to produce THF from butane. But uh, you know, we will see later that in any process, especially in many processes, including in biomass conversion, for example, in catalytic gasification, or even in biological conversion of biomass where enzyme is used, catalyst is very important. The catalyst is which is used inside the catalyst is really a kind of game changer. So always making a good catalyst for any process is important. This diagram is really interesting. It's very important that you keep in your mind. Uh, in any process, in any chemical reactor, it doesn't matter, chemical, thermal, biological. You know that we have two terms. One is selectivity, one is conversion. And always you have this kind of trend. If you want to have high conversion, you end up with a low selectivity. But if you want to reach a high selectivity of the product, conversion of the feed is always low. So always selectivity and conversion are in opposite trends. Therefore, there are a lot of activities in order to really reach a kind of catalyst where you can end up with the zone as I'm showing you here by this kind of red oval. where both selectivity and conversion can increase together, so they don't have the opposite trend. So you can see that in, I mean, in general, there are a lot of efforts in research and development to make a very good catalyst where you can have high selectivity and high conversion. As a result, for example, if you look at this diagram for this THF process, this is just about R&D cost. It started from 1980 until 2000, where research and development started from scratch until the commercial point. About $100 million was consumed, you know, in order to make a good catalyst, in order to then design the reactor and so on and so forth. So imagine this amount of money was consumed. But after the plant was built, due to some technical issues, the plant didn't work. And after all that money that they spent, at the end they had to demolish the plant. You can see that. This is the real story. Such a large industrial plant was built, and at the end, just they just threw away all those money that they spent. So you see, process scale up was very unsuccessful. Another uh, another story is about the case of CO2 capturing that you see here. In the boundary down system, it was there are two news in October 2014 and October 2015, exactly 1 year after. The boundary down system is designed to capture 90% of the CO2 emissions from one of the power plant units, the equivalent of approximately 1,000 tons of greenhouse emissions annually. The captured CO2 is compressed and injected underground to enhance oil recovery at nearly at the nearby Weyburn oil field, where for a cost of $549 million. Imagine such a CO2 capturing process was built for this a huge amount of money. But in 2015, there was another story. SNC-Lavalin built carbon capture facility has serious design issues. So this is a system that was built for almost one half a billion dollars had serious issues. The president and CEO of the company admits there have been many technical problems during the projects, which have resulted in the facility running at just 40% of its capacity. So almost half a billion dollars was spent, but only 40% of the plant could be used, and that's a huge loss of money. Okay, talking about process scale up, you know that we have a lot of parameters that we have to deal with, including in biomass conversion. Doesn't matter in any chemical process, you have feedstocks, different feedstocks, especially in biomass. You have variability of composition, stability issues. For that, given all sorts of different feedstocks that you can have, another issue that you have to solve is really to make a catalyst that can perform well and it has a good support in order to have high conversion, high selectivity, and a promising life cycle. Another important issue is about the reactor itself. So that's why a lot of efforts are R&D efforts are spent for optimization of the reactor hydrodynamics in order to enhance heat transfer, mass transfer, to understand the gas liquid solid behavior and how the contact between all these phases impacts efficiency of the reactor. Another important sort of parameter is about process operation itself, including, in terms of separation, inventory corrosion, control, and so on and so forth. So there are a lot of efforts that you have to do in order to have a successful process scale up. Okay. So that's why you can see, for example, for this case of a circulating fluidized bed boiler, uh, see, you can see almost 30 years was assumed in order to make the process to reach a kind of um, running at commercial scale. 30 years, imagine. So it's too long time. If so, you can see the process scale up can be very, very time taking, and at the end it could be completely failed. That's very important. So you see, when you go to the lab, like you go to your lab, you just add your materials and in a small reactor, and you do some tests. You just use your reactants. You just heat up your reactor, for example. You get your product, and then you publish article or you publish a report, and you think it's bingo. No, but if you want to really expand this lab reactor that you deal with at a larger scale. In fact, as we discussed last week on onion model of process development, you have reactors, but before reactor you have some pretreatments, and after reactor you have separators, including all those heat exchangers, utility systems, and many others. So you can see that uh, the process that you develop at the lab scale compared to process that you are going to develop at the larger scale they are very different, more complex. So process scale up is really a huge job, and that's why it can take a lot of time, a lot of optimization, a lot of corrections, a lot of efforts to reduce the risk of the operation. Also, things about safety, environment, everything. But let's see why many process scale-ups have been unsuccessful. It's because, as I have shown in this diagram, because traditionally, when people want to scale up, they use a kind of linear approach for process scale-up. In other words, for example, as shown here, after companies develop a process at lab scale, okay, they just decide to scale it up and make a pilot. They make a pilot scale. So you know that pilot scale is a usually pilot scale is the kind of process. It's not industrial, but it's a process that really includes most of the unit operations in any process. I mean, it's a kind of prototype of the commercial process, but at a larger scale. So people make that's why people they don't go usually from lab scale to the industrial scale, but they just build a pilot scale based on the lab scale process. After they made all those optimizations at pilot scale, then they start to think about a scale up to commercial scale. So they build a commercial plan. So there are many different techniques that are listed here for process scale up with linear approach. But actually, according to methodology that we are developing at Polytechnic Montreal, especially by a kind of work that is being led by Professor Shauki, is iterative scale up approach. In fact, we are writing a book on this methodology, but it is important for you to just get an idea how this scale up approach works. So in future, if you work somewhere, you can have an idea how this works. So as I said, Traditionally, people make a lab scale and then they go to pilot scale, then they go to industrial scale. But we we are developing a methodology where from lab scale directly we go and design industrial scale. Okay, but there's a big but just virtual, not real. So, in other words, we use simulation here by different simulation techniques. For example, by Aspen Plus, by Excel, by CFD-DM simulations. CFD means computational fluid dynamics. DM means discrete element method. These are for simulating hydrodynamic and multi-phase systems. So by using different simulation tools, in fact, uh, we use the lab scale data, experimental data that we have obtained at the lab scale, and we simulate the process, a real process at a larger scale. Let's say, for example, 2 million pounds per year of production of product. We simulate it by these simulation tools. In other words, what we do is that based on lab scale, we generate a couple of process flow sheets, not just one flow sheet. We generate different flow sheets by simulation, like for example, Aspen or HISIS, and then we apply techno-economy analysis. Okay. Also, we apply CFD-DEM, multi-scale modeling, or different sorts of modeling that exist in order to really virtually observe how process can look like at a larger scale. Okay, but it's just virtual. It's not a real process. So after we do by simulation, after we generate this kind of virtual commercial process, then we identify what kind of problems, what kind of missing information, and what kind of risks are there that we could not identify at lab scale. In other words, by simulation, we generate some questions. Okay, for example, should we use uh, shell and tube heat exchanger, or should we use a boiler or condenser? Should we use a fluidized bed reactor, or should we use the kind of rotary kiln? Should we use, for example, let's say a distillation column in the process, or no, because instead of distillation we use another separation equipment. All those uh, things we do it by simulation. By simulation, we all we really investigate all these flexibilities for the process. Uh, then we raise some questions. For example, um, okay, if we use a distillation column instead of if we use a distillation column, for example, instead of kind of absorber, for example, uh, is it really possible to do it, to operate it in a real world, for example, or what kind of issues in terms of operation we could have? Maybe simulation gives you some good, interesting results, but is it really possible to do it? So anyway, by all those simulations, we raise some questions. And based on those questions that you raised after simulation of the industrial scale, you go back to lab scale and you go to lab scale and you start new experimental work to find answer to the question you raised at the industrial scale. Or maybe you don't go to lab scale anymore. From industrial scale, you go to pilot scale. in order to find answer to those questions that you raise at the industrial scale. So either you go back to lab scale or to a pilot scale, you get new data, and then you implement those data again to the simulation tools that you have generated before, and you so again you re-simulate your industrial scale to see to really find the process at a kind of a more optimized form. So you always you go through this loop that they call it iterative loop. So by lab, you do simulation to industrial scale, you go to pilot or lab, and then again, you go to simulation. By simulation, you go to industrial. Again, maybe at the second round, again, you have some new questions. To answer those questions, again, you go back to pilot or to lab scale. So you really practice this kind of iteration loop until you reach a industrial scale, okay, industrial scale at a virtual form where you have the minimum kind of uh, number of questions. So you are comfortable that the process now looks more realistic, and based on which you go and make your uh, pilot scale, and then uh, in order to make your the demo, and then you may build up eventually your industrial scale. So you can see that simulation that I have shown by this yellow arrow is extremely important. So you know that nowadays, for example, in NASA, they are doing a lot of research in order to, send the rovers to Mars, to other planets. All those kind of things are done by simulation. They cannot just build something and then send it directly to Mars. They do also a similar approach. They have to do simulation. So at the simulation environment, they have to really consider all the risks, and then start to build a real plan. So we believe that by this kind of industrial scale up, uh, the failure of the process is going to be minimum. So the good news is that you know that simulation is based on computer, right? Like it's a computer aided process design. So it takes a lot of CPU and data storage and cost of the, uh, computation. So the good news is that if you look at these trends, the cost of data storage is much less than 20, 30 years ago. I remember 15 years ago when I first when I first saw a real hard drive for 1 gigabyte. I could not believe 1 gigabyte. Wow, and it was very expensive. And now you can buy a much bigger the hard drives and much cheaper, right? So data storage cost is much less. And on the other hand, the CPU speed has been increased compared to 40, 50 years ago. Okay, and that's you can and accordingly you can see that in this curve. So a lot of while efforts in process scale up is increasing, also you can see that the using computer for process simulation is also increasing. So this shows that if people they tend to use simulation more and more for their process scale up efforts. So this was basically the message that I wanted to provide you. This is something interesting. We are writing a book on this topic, so it's a really kind of fresh uh, kind of information for you, and I hope you enjoy and you take this kind of iterative process scale up for your future work. Here is a kind of a fellow sheet how to use the process scale up by iterative method. I don't want to go to all details. It's up to you if you want to go and see. But basically, as I said, you do lab scale. experiment. Then you generate different failure sheets by Aspen Plus, by HISIS, whatever. So you up by then by simulation you do material and energy balance. You do a lot of um, process optimizations. Then you do techno economy analysis, based on which you identify some questions at larger scale. To answer those questions, you go back to pilot scale or to lab scale in order to find answer to those questions experimentally. And then you go to simulation back, get new virtual data, use it for pilot commercial scale. Again, back to pilot or lab, and this loop should be iterated a couple of times until you have comfort in your process scale of activities. So this was the discussion for today. I hope you enjoyed. I leave it now to